it allows to future-proof our designs in a way.
That's correct. Yeah.
Thanks.
But thanks for joining. So we can go to Pablo, for example, or anyone can jump in for the introduction.
In terms of cost and safety.
That's correct. Okay, but the oh, I can see him.
Yeah, yeah. I just had someone.
Okay, we did start recording. So in the beginning, I was talking about beginning out to.
There is like echo. If you can mute yourself from the
There is an
anyone
echo.
else. Yeah.
Does everyone hear an echo or only you?
Can you try again to see if there is an echo?
Does everyone hear an echo from me?
Now there is no echo. Yeah, you can go.
Okay, yeah. So in the beginning, I was just thanking you and the IEEE and University of Waterloo for this opportunity, and I'm always thankful for giving something back to University of Waterloo because I did learn a lot in it. And do you would like to make any introduction from your side, or should we jump directly to the topic?
Yeah, yeah. I just today we have Dr. Muhammad Kadragi. He's an expert in batteries. He worked in batteries in industry and research. He did collaborate with Wise Institute at University of Waterloo, doing research in energy storage. Muhammad generously accepted our invitation to give a talk about um, batteries, safety, and second life. So I will give the floor to Muhammad to introduce himself and start.
Yeah, thanks a lot for the invitation. And before I start, I have to mention 2 points. The first thing is that we are recording this session and it's going live. So if you want to use your mic, camera, anything, it's up to you. And the second thing is that I'm representing myself because at the end, we as experts, we are working in companies. So I'm not here to represent any company I'm working for. I'm just representing myself and talk about Arabic, which is my own pay back to the society. So whatever we're gonna share today is open knowledge. You can find it in the internet and papers and anything, and there is nothing related to the deep industrial things which I'm working on personally. So this is an important info before we jump into the topic. So the topic for today was discussing about battery life, aging, and second life. And it's a very interesting topic because it's a very complicated topic and becomes of high interest nowadays. And I don't want to give a lot of information from my side as much as I will give information from my side and stop and asking for questions. And please feel free to you write your questions in the chat or just unmute yourself and give any questions. Just there is no dumb questions. All questions are welcome. But as I mentioned, my main structure for the talk is that to give a brief introduction about what is happening in the battery world and just a basic introduction, and then we can jump directly to the value chain, the cell chemistry's effect as requested before we start the recording on the lifetime and the aging in different cell chemistries and those topics. Okay, so I guess you can see my screen, all of you. And if you cannot see my screen or if I hang it somewhere, just let me know. But uh, I will start from here. So yeah, any AV, this is, for example from Audi, has something which is on the bottom of a small AV electrical vehicle, which is the battery. And it's the backbone of the electrification of many EVs. Of course, there are fuel cells, but batteries are the main focus nowadays for the last 5 years. And this is one example of how a battery pack could look like. So at the end, the battery has many components inside it. What I'm trying to always simplify for the people who you are working in the battery field or not is what are those main components, what are the critical parts you have to look at, and the messages of that batteries are complex creatures, especially lithium-ion based batteries. They are not as easy as handling lead-acid batteries. And there is a safety and aging complex problems related to lithium-ion batteries and even the next generation of batteries will have some problems, whether with aging or with safety. For example, for a solid state batteries, it's much safer, as we will see, but at the end they will have problems in the life cycle. So the battery topic is not as easy as it looks from outside. And if we look at this here is a whole battery pack. For example, we have the cooling system of the battery, and not every battery has a cooling system. This is an automotive battery, so that's why it has a cooling system. But I know that some people from the audience are coming from the stationary storage. So normally in stationary storage, in a small battery in the home, you don't have a cooling system. You have a passive cooling, so there is no cooling at all because you don't want to lose your energy. In a container size, you have an active cooling. So it depends on the application. You have cooling or not, and this cooling could be water-based or could be air-based cooling. And the other part here is related to the, there's a question. Yeah, please unmute yourself and just drop it.
Sorry, that's my mistake.
No problem. And you have here the modules, and inside the modules there are many structures which will come inside, which are the cells itself. And the cells differ from chemistry and from the way it looks like, and both of them, which we call cell format and cell chemistries, has a huge influence on the battery performance. And we have the power electronics, the high voltage part, because those batteries nowadays are not only 48 volts. So above 60 volts DC, you are in the high voltage, which is risky for our lives as human beings. So batteries nowadays has 400, 500, 600 volts DC. And that's why the high voltage topic plays a big role, and the battery management system and the main brain of the battery of controlling it. So this is very fast, the components, but of course, as I mentioned, in depth, it looks much more complicated. So before we started the webinar, there was a request about have a look on the battery chemistries, and from especially the cycle lifetime and a cost perspective. And this is a very, I would say, complex graph, but let's simplify it. So we have here LFP, NCM, and NCA, which are three different cell chemistries from a lithium-ion battery-based cell chemistries. So LFP refer to lithium iron phosphate, NCM is nickel, cobalt, magnesium, and NCA is nickel, cobalt, aluminium. And this is the cathode material. Just for simplification, each battery has a positive and negative sides, and in lithium ion, more or less, the anode is graphite, so it doesn't differ from one cell to another, but the cathode is what you can see, what you see the names here. And LFP, NCM, and NCA, I guess everyone who nowadays interact with batteries hear those names. At least he hears about LFP cells. If you asked someone like 2-3 years ago about LFP or NMC or NCM, he will never know that this is a subcategory from lithium-ion battery. But now people are starting to get crazy about batteries in social media, distributing knowledge and so on, and that's why it's very well known now with those subchemistries. And there was mentioned as well sodium-ion batteries. So sodium-ion batteries is another type. It's not lithium-ion based; it's a sodium-ion battery. And there is the old solid-state battery, which could be lithium-based battery, but solid-state. And we will come in a minute what is the difference between a lithium-ion normal battery and a solid-state battery, which is lithium-based as well. And there is the classic lead-acid battery. And I did this comparison myself to really compare different technologies in one place. So if you look at the gray graph here, if I move with my mouse here, this gray thing here is the classic lead-acid batteries, which, for example, used in cars, or there are even subcategories of lead-acid batteries. I'm talking about AGM lead-acid battery. What you have in the car mostly will be gel or AGM battery. There are flooded batteries, which before we had to put water inside it from time to time. So the lead-acid battery, they are cheap, for example, but their cycle lifetime compared to lithium ion is very bad. And their efficiency as well, they cannot carry a lot of energy. They are very heavy from the power density and the gravimetric energy density. And the power density means watt per kilogram. Energy density means watt hour per kilogram. And what you see here is that this is the classic batteries graph. And that's why this is one of the main reasons. If the graph is to the center, it means that it's a disadvantage. The more it's outside, it means it's an advantage. So 5 out of 5 minutes, it's super safe battery, for example, or highly safe. So that's one of the main reasons lead acid batteries are not used in electrical vehicles, because they cannot carry a lot of energy. They are very heavy. And that's why we have lithium-based categories. If you compare this spot here, or let's talk about battery power density. If you compare this spot here to an LFP, which is here, you will see, for example, that LFP can carry maybe 2-3 times of what a lead acid battery can carry on watt per kilogram. So if you have a 1 kilogram of a lead acid battery and 1 kilogram of an LFP lithium ion battery, or if you have a 1 kilogram even of an NCA lithium ion battery, you can really put maybe 5 times the energy here than you can put it here. And that's one of the main reasons what makes lithium ion based chemistries like LFP, NCM, and NCA very attractive for applications like electromobility, because you have a very small size and you need the car always to be very light. But if we talk about stationary applications, there are still stationary applications, big applications using lead acid based technology, lead acid batteries. But they are not very attractive. And you can use them because you have a space and you don't care about the weight. But in terms of lifetime and cost, really nowadays you can get lithium-ion batteries which, in a cost comparison, much better than a lead acid battery, especially for LFP chemistry. So you can get a lithium-ion battery which is cheaper maybe than per kilowatt hour than a lead acid battery. So there is no motivation to use lead acid anymore. Still, lead acid exists in some niche applications like UPSs and so on, uninterruptible power supplies. But really, the future is more or less, or they always say battery is the future, but battery was the future 5 years ago. So using batteries, lithium-ion batteries, is a current thing which we cannot resist. And there was a question about sodium-ion batteries as well. Someone mentioned it. If you look at sodium-ion batteries, the first generation of sodium-ion batteries came from CATL. It will come in a minute. But each type of chemistry, I will not dig into details. We will get back to this curve if we have time. But as you can see, each type of a battery has its own advantages and disadvantages. So this is only from the chemistry perspective, and this is very generalized as well. If you look at subcategories of solid-state batteries, if it's sulfide solid-state or polymer solid-state, there will be a difference into advantages and disadvantages which can bring you in. So there is always, even LFP have subcategories inside it. If it's a nano, how you structure your cathode and so on. So do you put some of nickel, magnesium inside it? Is it LMFP or a pure LFP? So there is always a stage of depth. But to make a general comparison, the main message here is that each chemistry has its own advantages and disadvantages in terms of cost, cycle life, safety, efficiency, and so on. Those are the factors which I selected to make a comparison for. But one of the main issues or factors which we are discussing in this webinar and focusing on is the safety. And I don't know how many of you can just use the raise hand in the chat. How many of you did hear that LFP is a safe battery or a safe chemistry? Did you hear this? I see someone is raising the hand. Perfect. Can you unmute yourself and tell us what do you hear about this, or what is your opinion about this, or what you are convinced about? LFP is safe?
Yeah, so the common understanding is LFP is more thermally stable than NCM. So which means that they are less prone to cause on fire or have thermal runaway.
Yes, thanks very much. This is the most accurate comment I have heard from the market so far, because people think that when we say that LFP are safe, they are safe in general. They do not go to thermal runaway. But this is wrong. They are we can say, as have been mentioned, LFP is safer than, for example, NCA particularly, or an NCM, because they go into thermal runaway in 50 degrees plus higher, or there are some structures of LFP which facilitate in thermal runaway what we call vapor clouds or white vapors more than going into fire. So a thermal runaway means that your cell is out of control, and in LFP, in some cases, you have just the white smoke. Although this white smoke, from my own perspective, is much hazard or much dangerous than the fire itself, but people are interested in general if they are not having this expertise into fire. And that's why LFP, we can say it's safer than other chemistries in terms of thermal runaway, but it's not a safe chemistry or a safe battery. We cannot claim it like this. And the solid state batteries, for example, has a big, that's why I put it here on the scale of safety on 4. But if you look at sodium ion and solid state batteries, this is where really you have a big advantage of safety, because in that case, you can have a cell which doesn't go into thermal runaway. It doesn't produce any fire. And this is a big advantage. But as I mentioned, you will have problems maybe with the cycle lifetime versus the LFP cases. So I know that this point here is very important for some of you. So if anyone has questions related to this, please let me know, or otherwise we will get back to this graph in a minute. Or after we...
Just a question about the source of information of this graph.
This is it. No, I'm kidding. The source of information is that based on, I really gathered my own experience, plus all the literature I did find really evaluating cell chemistries. So I did list the sources in the end of my presentation, but there are a lot of literature review which I did myself to gather this information, and plus what I did see, because I did battery testing myself, and I did see the effect of having this chemistry on this amount and so on. And to be honest, this graph is very dynamic because we have changes every day, for example, in the cost perspective. So did you get what I mean with the source? It's not only one source. I did really, I guess if we list the sources here, it would be maybe going to 20 sources or something like this. So I did look everywhere that anybody has a spider, we call this spider diagrams, everybody had a spider diagram, and did really create my own impression out of it to make it realistic, more or less. Did this answer your question?
It's a mix of academic and industry.
Exactly. Yes. 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 And that's why I made my own graph based on what I see in many academic literature plus the industry experience.
Does this, for example, take into consideration specific products, like, for example, the blade battery from BYD, which is mechanically much more safer, or just on a general chemistry perspective when it comes to safety and liquidation?
Yeah, but the blade is not a cell chemistry; it's a cell format, and this is the next topic.
Yes, that's what I meant. So,
yeah,
is this focusing on the chemistry?
This is
of how you are using it when it's come to the product, or you taking the product its aspect in that, because, for example, this blade product is purely LFP, for example, which might affect the common knowledge of or how you see LFP as a chemistry.
Yeah. In few minutes, I will show you the same spider diagram which I generated as well for the different cell formats. So there is cell chemistry and cell formats, and combining both together, you can have something like the effect of LFP blade battery or LFP cylindrical cell, and you can compare them together, okay? But this is a very good question, because at the end, people talk a lot about cell chemistries in terms of safety and aging, and they neglect the cell format as well, or the cell structure. And we have to always take both of them into consideration.
Yeah, thanks.
No problem. Any other questions? Okay, so as I mentioned, there is not only lithium-ion batteries, but there are a huge amount of batteries that we know along 20, 30 years of lifetime. So we have lead acid batteries here. This is the volumetric energy density, and this is the energy density per kilogram. And as I mentioned, lead acid batteries, they are not very attractive for many applications. Lithium ion, as you see, is sitting in the middle of the graph, more or less. There are lithium air batteries, solid state batteries with lithium metal are here, which is lithium based, as I mentioned. There is sulfur batteries as well, are having a lot of development nowadays. Magnesium is getting into lithium much more. You can hear about sodium ion batteries from CATL, namely, for example, aluminum batteries. There are many different types of batteries which you hear about every day. But from industrial perspective, from practical perspective, not from research perspective, what we have in the market is really the lithium ion push, the sodium ion, namely from CATL specifically. Lithium sulfur is getting into the game, so there are we are seeing in the market some cells from lithium sulfur based, and solid state battery has a very high attention and industrial pressure. The other chemistries are interesting, but still in the, I would say, the early research or in the second layer after those chemistries here. And there is lithium ion and lithium polymer batteries, but I will skip this and get to it maybe later, because we will discuss about lithium ion. But in terms of applications, and this is very important, that using of batteries in gigawatt hour per year gets really exponential. So this is 2021, and you can see that maybe more than half the capacity we're using it in passenger EV cars. This is the main application of batteries. And if you look at stationary storage, it's just this small slide here. Consumer electronics comes next after passenger cars of using batteries on the planet globally. This is from Bloomberg report last year. So that's why it's one of the main drivers for this technology is the passenger cars, namely the electrical vehicles. And there are many types of EVs. So when we say EVs, it's not only the passenger car, which you see here. There are scooters, e-scooters, passenger cars, vans and trucks, 2 wheels and 3 wheels. But as you can see here, buses, in terms of EVs, are the biggest share of electrified battery-based application. So there are a lot of electrical buses on the road already, followed by 2 and 3 wheels like e-scooters, e-tuk-tuks, e-whatever runs on 2, 3 wheels, and passenger cars, and the last thing is vans and trucks. And they are all getting electrified, but as I mentioned, buses got it electrified very early, and that's why there is a main focus on it. And as you see here, this is the market expansion, or the market. Sorry, I have to close this. This is the market share per country, and of course, most of the EVs comes from China, and they are distributed in China as well, followed by the US, Germany, and so on. But you can see how much consumption there is and how much production is in the Chinese market. And that's what China is one of the main leaders in this industry as well. I would hide this and ask you the question: how much do you think the share of a battery inside an electrical vehicle structure? Just make a number in your mind. I will show it in a minute. But if this number is less than 50%, then you are wrong. So the share of a cost of a battery inside an EV, it's about 40 to 50%. And that's why the battery itself really can play a major role into making the EVs really economically viable. And from the electrical vehicles, there are battery-based electrical vehicles and there are plug-in hybrid, but plug-in hybrid vehicles are getting less and less in the market. So we are seeing a lot of battery-based electrical vehicles in the market as well, like from many brands available in the market. And this is a very, very nice overview of, what is an electrical vehicle, or how we electrify vehicles, plus the brands working on it. This is not an exclusive brand. There are many other brands working on this, and this is mainly for the passenger cars, the passenger EVs. And as I mentioned, there are battery-based and there are fuel cells. And each one has its advantages and disadvantages over each other's. I guess we have or me personally, I have been talking a lot with fuel cell experts about this comparison. But as you see here, there are many brands working on battery electrical vehicles, and there are few brands working on fuel cell electrical vehicles. And this is really something which we can see clearly in the EV market. And the reason is that fuel cell EVs in a small size, they have many challenges inside them. I guess we can cover them in one of the next seminars, the comparison between both. But this is a very famous graph from Toyota, which they made it clear that depending on the travel distance and the vehicle size, fuel cell make sense in big applications like buses, long distance trucks, and so on. But for passenger cars, they are more or less battery based. But as I mentioned, let's discuss it maybe in the next seminar, the hydrogen things. And of course, one of the other applications which is common is having a container full of batteries. This is a common application, but this is one of the most important things which I like always to communicate is the battery value chain. And by value chain, I do mean that there is steps. There are many steps which going from mining to having battery material to cell production, unless you have a battery, and BOL means beginning of life. So getting a battery really has many stages before, and each stage has its own complexity and its own know-how as well. But the main thing which you see here is that from mining, you can get to cell production to a battery, and then the battery started to be in a specific application. And this is where the battery starts to operate. And this is where data as well comes into the game. So operation data from batteries on ground are like treasure nowadays. It's something which we build something called digital twins for battery. And this is one of the key things which we understand aging with. So without data, really high resolution data and very detailed one, from even production, from the early stages of the value chain, it's one of the main things which you cannot really have a clear overview about the aging and the safety status of your battery. This is one of the main messages I have to give here, even that giving it quickly, and maybe we can discuss it in details afterwards. But after you have the system operation, whatever your system is it a battery container, is it a bus, a truck, a passenger car, or whatever, you have two options. You have end of life, or you have a second life. And as well, if you can use the hand thing in the chat or just unmute yourself, how many of you did hear about second life of lithium-ion batteries? The term second life itself? Okay, I can see. Okay, so the second life, in general, it means that we are using the batteries from the car application mainly in their second life after they fulfill certain criteria and they have still a bit of energy for stationary storage. It looks like a very basic idea, a very logical idea, but it's from a battery expert perspective, it's a very complex and dangerous idea at the same time. Because to say from a safety perspective, even in the first life, even here, we still have safety problems nowadays, which we are trying to overcome. And we still have complexity into understanding the safety and aging status of a battery. So you can imagine how much this would be much more complicated in a second life application. So especially with the lacking of the standards. So we don't have so many standards. Standards are developing, and beginning of 2030, 2032, there will be a new UN standard as well in the market, which will really be very restrictive than the ones which we have nowadays. So for a standard to come into existence, it's like 5 to 7 years. And today, because we have a lack of standards, everyone can do whatever he wants. There are very few standards, so someone can get you a battery out of a mobile phone and tell you, okay, some batteries, I will connect them together and give it to you as a second life, which is at the end is creating a problem, not a solution, because at the end it's a very critical thing, and there is no clear KPIs. But there are some standards from the UL which have been developed recently to control the second life and to make it a bit under control, what KPIs to be used and so on. I will come to them in a minute. But there was a question in the chat. I can, if the one posted can just say it, it will be much better, much easier for me. I can see, yeah, I can read it. It's explain how the knowledge of production details affects the degradation estimation. This is a very nice question. I guess he means here in the cell production, for example. And let's give a clear example about this. General Motors from last year, beginning of last year, if I remember correctly, had to make a recall and pay $2 billion for this recall. And this is a clear example of, for example, degradation safety, because at the end, GM by this time have taken the cells from LG Chem, which one of the most well-known cell and high-quality cell manufacturers. But the root cause announced was that they had a problem in tapping inside the cell, which one of the steps of this cell production. So tracking back this data led to the root cause, which happened due to aging effect after the cars were already on the street. As well, if you have, for example, certain existence of humidity or certain existence of dust or certain process which have not been controlled in cell production, or even logistics, and even getting the battery from one place to another, and you have a shock or something like this, those things affect the aging, but you cannot see them from day one, and you cannot even measure them. You will see them in a form of degradation or thermal runaway or safety issue after maybe 3 to 5 years of operation. And if you don't have this knowledge from before, you will never be able to track the root cause, and you will never be able to expect that, okay, for example, this container have exploded, this one will explode or not. You will never be able to do this. And that's why we started to realize that the importance of the data along the value chain. I'm trying really to simplify the answer of the question here because of the time, but we can discuss it in more details when we open what can happen in aging in general. Is that a satisfied question answer for now, or?
Yes, I understand. Then it's a matter of faults within the production process rather than the production method. Because from other products, like if I can borrow from other industry, like the PV modules, how you manufacture them, if it leads to a different performance efficiency, as in a systemic way, it's not the fault. What you're talking about is during the production, if the production itself is not conducted to its own standards, it can lead to further effective degradation.
Exactly, and you cannot mark it as in PV. In PV, it's a direct relation. In batteries, it's not a direct relation.
Okay.
Yeah, this is the complex part here. But thanks for the question. So in general, this is just an overview about the amount of companies which are involved in the battery industry. This is not all of them, but this is just some of them, just along this value chain. You can see there are companies only for mining, companies producing only electrolyte, anode material, cathode material, and those are the kings, by the way, the cathode material production. Companies doing only quality control and data analysis, grid systems, second life battery technology. So the companies, even the big ones, are very, very, very concentrated and specified. So it's not only one person who, even Tesla themselves, which are here, they have to combine a lot of things out of those here to be able to provide their own production. each other company have to do this. Volkswagen, BMW, each other company have to combine this. But this is just to give you an overview that it's really a lot what is happening in the background in order just to manufacture a battery cell and put it into an application. And unfortunately, we have some examples which this is one of the things which I have been sent from one of my colleagues in a country in the Middle East. I guess it was Dubai, in the Dubai Mall or something like this, where they have superchargers inside the mall parking itself, and it looks very nice. No one can say nothing against it, but this also can happen. And you can imagine this happening inside the parking, because this photo here, I guess it's clear that it's winter. But if you have sharp eyes, you will see that this is a Tesla supercharger. Because combining fast charging with the wrong conditions of weather can lead to a thermal runaway. And I don't have any idea if a thermal runaway happens to one of these cars inside the parking here, what will distinguish this? Because everything you can install inside the parking is not enough to distinguish a fire from an EV. The only ways which we handle EV fires is that we take the whole battery, the whole car, put it in a container and leave it maybe for 3 days. And a container full of water and solvent to make conductivity. And even afterwards, the risk, it goes into a thermal runaway. So you always need to call the firefighters, tell them, okay, I have this. They have to come take the heat somehow, but you cannot do it yourself. And that's why when I see those things, it's like seeing a horror movie for me. It's not, my friend did send me the photos out of saying, okay, what do you think about this? It looks fancy. But once I started explaining him the risk, he said, okay, you are correct. I will not pass by there. It could be that they will stay for a couple of years without happening anything or over the lifetime. But I mean, the concept itself, that we have to be conscious about what we are doing. And there was a question before we start the recording as well about the recommendation of using EVs or not. It's not that I do not recommend using EVs, not that I do not recommend using chargers. It's that we have to use it in the correct manner. Otherwise, the problem is not the lithium-ion battery, because a lot of people say lithium-ion batteries are not safe. No, they are stable. They are safe until you abuse them. And people, because of lack of standards, they are really getting very creative in how they abuse a lithium-ion battery. And at the end, they say, okay, the lithium-ion battery itself is not safe. I guess this is the clear message I can give here. And one fire of a lithium-ion battery, there is a question here. If you can unmute yourself, just say it directly, or I can read it as well. Would you like to unmute yourself, or I read it? I will start reading it, but you can as well. But thermal runaway can happen even when the batteries are not charging. This is totally correct. So I did not say that thermal runaway is happening only while charging. Thermal runaway can happen even if you're not charging. That's right, but the possibility is different. I will show you in a minute the answer for this. Maybe I can jump to the answer of this question, because it's very interesting. Because I made a survey myself just to answer this question for myself. So this is a survey which I did. I guess I published it into 2001, 2002 of when does the thermal runaway events published so far happens. And you can see here the biggest portion is fire while being parked. This is not charged, this is not discharged, just parked, but just in the parking without touching it. The biggest amount of incidents I did really find myself is that it did go on fire while being parked. This is while being charged. This is the second position. Post crash, so after a car has a crash, it goes into fire, but this is something expected. There is as well fire being on the road. Some people had incidents that they are just driving the car and then it goes on fire directly. And then that's why the new regulations especially in China, has 5 minutes of escape time. They put it in the regulation, and others start to follow. But just to comment on the question, you are correct. It can happen while not charging, and that's why it's not in some countries like Australia, by definition in standards, you are not allowed to put a home storage or a battery in what they call it a living area. Like you cannot put it in your bedroom, you cannot put it in your living room. You have to put it in a non-living area, which means, for example, your garage or something, that if something happens to it, if you abuse it somehow, this place is outside, there is access for firefighters to it, and it will not harm your own life. But you can imagine putting a lot of electrical vehicles into closed garages. This is an idea which I see it really funny to do this. Did this answer your question? Or if you have a follow-up question, just write it inside or let me know, please. So I will, yeah, and it was announced maybe, I guess, few months ago that on average 7 electrical vehicles per day goes into fire in China from many different brands. But this is totally normal because we are in a industrial transition. But the good thing is that if you compare here, this is a very nice comparison of a Tesla per mileage going on fire. And if we compare EVs per mileage to even normal cars, the EVs really does much better in terms of mileage coverage than on average vehicle running on petrol or gasoline or something like this. So we hear a lot about incidents because once there is an AV incident, it's coming into the media and so on, and it's a new technology and so on. But we stop hearing about the normal car fires or the other fires because the technology is much mature and so on. So we're getting into maturity, and you hear a lot about Tesla going on fire on YouTube, on LinkedIn, on the media. But this is not because Tesla is bad, for example, or any brand is bad. It's because of that those brands who really knows how to build batteries, they are selling more. Especially this applies to Tesla, for example. So Tesla sells more than the last survey I have seen, half the market share of EVs. And that's why they are selling a lot. That's why you can hear about thermal runaway and safety events from them a lot. So I don't want you to mix the issue of that, okay, cars are getting on fire and so on, that they are not safe. No, per mileage, they are safe. But as I mentioned, the problem is not the battery itself, the technology. The problem is mainly how you use your car, how you use your battery. I have seen videos of people driving their EVs in a crazy manner. Really, they are simply breaking the laws of physics. and they say, okay, the battery is not safe at the end. Yeah, so this is something which I wanted to highlight about the safety incidents. And to put a battery on fire into really safety, this is one of the things or best practices. This is a Tesla going on fire. And as I mentioned, we hear about Tesla because they have a big sales amount. And really the fire aggressiveness is very, very high. So I will skip parts of the video just to see. This is what remains out of the car itself. And you need a huge amount of water. You need to use, if you use water, and water is one of the things which we use to distinguish lithium-ion battery fires, but we don't use it in small amounts. If you use the small amount, you are really making the problem much worse than it is. You have to use a huge amount of water. Like this one, swimming in a lake of water. Really, I don't know how many tons of water have been used there, but if I remember correctly, it was 40,000 plus liters or something. I calculated once. So you can imagine this is happening in a closed parking lot. I guess it will not be a funny thing. at all. Because the problem is in the thermal runaway event, the energy comes from inside the cell and the oxygen comes from inside the cell itself in many chemistries. There are chemistries which produce less oxygen, like LFP, but there are chemistries which produce a lot of oxygen, and that's why you cannot easily distinguish a fire of a lithium-ion battery. And you hear about people. I have seen crazy things going on social media. People simply saying, "Okay, you can use sand on it. You can use whatever on it. If you can use," and sometimes I really have to stop them and tell them, please don't do this. Don't give false information which can cost someone his life. Because the only rule which I always recommend, if you see a battery fire, if you see the white smoke, please run. And people think that the bad thing is the black smoke. No, the black smoke is good. If you see it white, you have to run very fast. If you see it black, you can run in less tempo. But if you see a white smoke, you have to really leave the area very, very fast. Yeah, there are more information. I put it on my YouTube channel. You can easily check it. I talk a lot about battery safety and many aspects. It's in Arabic, but we will do an English subtitle for sure. We have been requested to do this. But as I mentioned, there is a main difference between what you see here on the left and what you see here on the right. And what you see here on the left is a common structure of a conventional lithium-ion battery. This slide is from QuantumScape. And what you see here on the light is a lithium metal-based solid-state battery. And the first thing you see in comparison between both of them is the size per cell level. It's almost half the size because we call it an anode-free battery. So there is a cathode and it's solid-state electrolyte, not liquid electrolyte. And the liquid electrolyte is one of the main unsafe things which give us a lot of problems during thermal runaway event. And in the first charge, you have the lithium metal anode, which then make the solid-state battery. And solid-state batteries are a very promising technology. They are very energy dense technology. You can have fast charging for them without having many problems as you have with conventional lithium-ion batteries. But they have a main issue which we cannot overcome. They have many issues inside them, but one of the main issues which we cannot overcome them, maybe if someone can write it in the chat or someone unmute himself and if he knows the information, but the main thing which, yeah, we always make a joke. We say each lab and company tries to develop a lithium solid metal battery got burned in the last 30 years. It's because of the internal short circuits. There are dendrites of lithium, accumulation of lithium, which goes penetrating the separator, basically, and making an internal short circuit. And then the energy is not controlled. Then you will have a thermal runaway or a fire event. Many companies are working into solid-state batteries. There are many types, even of solid-state electrolyte used, even cathode materials and so on. But this year we have seen that some companies started to deliver even like the first samples of serial production cells. It was announced that QuantumScape, for example, this company works with Volkswagen. Solid Power works with BMW. So the big OEMs always have strategic partnerships with the solid-state battery companies as well. And this is something, if it becomes mature, it will benefit us in terms of safety a lot, in terms of aging as well. But the number of cycles you can get out of a solid-state battery is still low compared to a conventional lithium-ion, for example, LFP. And if it's becoming mature in electrical vehicles, it will become mature as well afterwards in stationary storage applications. I will skip this because of the time, and then what I wanted to show here as well, this is the basic structure of a battery itself, how it works from inside. So I will really skip all of this. Maybe we can do it. I don't know how much we are doing in time. Dr. Nassar can tell us if I can.
Yeah, we are booked for 2 hours, so still have time.
Okay, perfect. I guess the audience are not bored enough, so we can continue. But this is one of the points which we did discuss as well in the beginning, was the graph of the cell chemistry, which is the cell formats. I guess there was a question, if I remember correctly, about this, and we have given an example of the blade battery from BYD or any other thing. But looking at the cell chemistry itself as one part of the equation is not correct. You have to look on the cell chemistry and the cell format, and even you have to look on each step of the value chain, because at the end, if I can go back here, the whole value chain plays a role into having a safe and reliable battery. Not only that, if you have the best cell in the market and you integrate it wrongly in a module or a pack, then you did nothing. And if you cannot design your application correctly, if you cannot monitor it correctly, then you have done nothing as well. So the whole value chain have to be done correctly in order to have really a reliable and safe. Maybe the parts which I skipped, maybe we can do it in a follow-up seminar. But getting from one cell a whole battery module, I will give you an example of a production line which I did develop or I did participate in developing myself during my time at KIT, that at the end you have different cells welded together, and there are many welding techniques, but this is one example of resistance welding used. And then from one cell you get a pack, a module, and at the end you end up with a whole battery system, which can be at the end used. And you can see here, I personally did develop this robot. I consider him one of my kids, or the robotic solution, together with the team in KIT. We worked together. And you can just imagine why we did choose to use a robot to do resistance welding, where in the market, if you have a power bank, more or less, if you open it, you will see that someone really did weld it by hand or used very cheap techniques of welding and so on. And this is an example of how you have to treat the cells in the correct way along the process to really end up with a reliable battery, even the first life, and safe battery at the end. If you don't do this, and nowadays, as I said, because of the lack of standard, there is a lot of things going wrong in the market, but there are a lot of people as well doing it in a correct way, but you have to pay for it. Then if you do this in a correct way, then you are minimizing your risk. The risk will not be zero, but you will be minimizing your risk into going into safety and aging problems at the end. And on the other side of the coin, there is this nice video from YouTube who are people producing cells in this very nice manner here, saying, okay, we're producing cells. And you can imagine that those steps here have to be done, maybe some of them in a clean room, in a dry room with minus 40 degrees. There is a very interesting quality assurance issues with hand here. So this is the coating done by spoon. And yeah, I guess I don't have to comment further on this. I guess you can imagine what I mean by that. This is a quality control by hand. Yeah, and it's I got the video from YouTube simply. So yeah, getting back to the point of cell chemistry and cell format. So a cell chemistry combined with the right cell format is just one part of the equation. And this was the message which I drove in the few minutes before. But people really sometimes neglect the cell format effect. And as you can see here, this is as well the same approach I used in spider diagram into collecting the typical 3 cell formats, which we have: cylindrical, prismatic, and pouch cells. And for example, the BYD plate is a type of a pouch cell. So there are subcategories of pouch cells, how big they are, how the jelly roll is constructed inside. There are some details inside it. But in order to give something simplified and can be generalized, you can see here that, for example, for mechanical stresses, cylindrical cells provide a very good mechanical stress. That's why some automotive companies use cylindrical cells in their electrical vehicles, prismatic cells as well, but maybe pouch cells is not very mechanically stable. Thermal management, energy density, volumetric energy, wide use in electrical vehicles. This is one of the criteria which I put it myself. Stationary storage. So in stationary storage, you will have different cell formats than in EVs, for example, and so on. So each cell format brings some advantages and disadvantages, plus the cell chemistry itself. But normally in the lab and in the early production, we start with pouch format because it's an easy thing. You can put layers and test a cell with it. And going step by step, we go to the prismatic and cylindrical format. And you can see in the market that if you don't know what are the formats, this is the cylindrical format, which looks like, I have one here, cylindrical cell, which deeply discharged. I can show it. This is, for example, a cylindrical cell. Not the best quality, but it's a cylindrical cell. And prismatic cells look like a triangle. Pouch cells, very thin, and you have them in many applications. And as I mentioned, this is not the only criteria which is to distinguish the cell formats with, but combining this knowledge with the cell chemistry, then you can design your cell for your application. And different companies produce different chemistries and different cell formats. So I will give here an example of, maybe let's jump to this. Those are the suppliers, some selected names from the suppliers, like Samsung, Northvolt, CATL, LGCAM, SK Innovation, SVolt, and so on. And you can see here which formats. Let's look at here which formats are those suppliers are producing. For example, CATL is common for prismatic cells. LGCAM produce pouch cells, very well known, and so on, and cell chemistries as well. So, for example, NMC, LGCAM is going as well to other chemistries. Samsung is producing prismatic and cylindrical cells, and NMC based or LFP based, and so on. NCA as well is produced by Samsung. So the big OEMs tries to really combine what they have as cell format and cell chemistry for their own application, and even having customized cells for their own whatever electromobility or stationary storage applications. So it's not like an open market which you go and have from the shelf something which you can grab and really say, okay, I have cells, I will put them together and put them into this application, it will work. Maybe nowadays we treat it like this, but it's not the correct approach.
Sorry, unfortunately I have to go because I have to go to a meeting, but before I go, just one question.
Mm-hmm.
On your list, you don't have BYD, and I know they are one of the biggest suppliers. Is this, there's a reason for that? I mean, in other words, do you have concerns over their product, or is it because I know they supply to the automotive industry as well? So I could be wrong.
That's correct, but BYD produce their own EVs as well, and and that's why they are overly consumed, I would say. So it's like that's why. But you are correct. So if we look at it's actually the upcoming slide. So here you see those are the suppliers. Like this is last year. Let's focus on this. This is 2022. This is 2021. But let's focus on 2022. Who supplies really most of the cells or most of the batteries? So CATL has like 35% of the market share. followed by LG Chem 14%, followed by BYD. And BYD overtook Panasonic, which is one of the well-known manufacturers, and I guess nowadays they overtook even LG Chem. So maybe half of the batteries which we have in our world comes only in EVs, comes only from two companies sitting in China.
Okay, well, thank you very much. Really, thank you for the generous share of information and the good presentation. Unfortunately, I have to go, but yeah, looking forward for future sessions.
Yeah, for sure. We will have some follow-up sessions. I guess we will continue a bit here, and then you can see the recording. But I guess it's worth it to not overwhelm with the information as well, and really make a follow-up session. So maybe I give one or two last information. Not all manufacturers are in the same tier. Not all of them are like having the same quality, more or less, and the benchmarking. So some are tier 1, some are tier 2, and so on. And this is from 2022. These things does change very fast as well. So even you can see a lot of EVE, for example, maybe now they are tier 1 and so on. But there are efforts to put some standards into manufacturing, especially because of the safety and the aging issues. And what I would like to show here is that even there are new ideas of integrating the batteries in the EV itself. So Tesla have introduced this cell to chassis concept, that they put the cells directly not on modules and packs, they put it directly in the chassis of the car itself. This actually is a photo that I have taken myself in the Berlin factory, in the opening of it. And this is basically to show that even that Tesla, they pay big attention to the cell quality as well. There is a lot of room of innovation even on the integration and data analysis and so on, as I mentioned, along the value chain. Okay, I would like to propose that we can stop here, because I will not be able to cover the thermal runaway into details, but I would love to cover one part of a thermal runaway which is important. In case of a thermal runaway, it happens mainly because of many factors. I like this slide here because it summarizes the main factors making really getting us to a thermal runaway in a battery. It's mechanical abuse, like penetration or a crash or something, electrical abuse, and this is one of the most cases which we are facing in the market, and thermal abuse. And maybe in the follow-up webinar, we can discuss more about each type of abuse. But at the end, if you have a thermal runaway event, you have smoke, fire, and explosion. And those are three different separate things. And people think that fire is the main problem, but it's actually smoke is problematic, or maybe over problematic than fire itself. And people think that, for example, this is a thermal runaway of a bolt. And you can see here there are white and a bit of dark smoke, which we call light clouds and heavy clouds. And the guy who's shooting the video was lucky that he was not standing in the wind direction. Now he's becoming more in the wind direction. And what is coming out of here, more or less, in most cases, it's a lot of hydrogen, which is explosive. So if there is a spark near to this car and someone is shooting a video like this, I guess you know what will happen. And some CO, like toxic gases for us, monodioxide, which can kill us, more or less, and sometimes hydrogen fluoride as well, but in small quantities. But because of the lack of awareness, this is the thermal runaway event without fire. This is just smoke coming out. And yeah, taking such a video is a high risk by itself. because whenever someone has to see this in thermal runaway, he has really to like go imagine that this battery will go on a fire anytime, and then you have really to go far away from it and call the firefighters, because even the firefighters sometimes they don't know how to deal with the thermal runaway. And but at least they are getting experience nowadays from the battery expert and battery people. And people think that, okay, this white smoke, maybe it's a water vapor or something that they know, but it's not. And he's trying to distinguish it with this small spray, and he doesn't know that he's making it worse by doing this. Because as we mentioned, if you use water, it's good, but you have to use it really in a big amounts to cool down the cell temperature and to try to control it. But if you are putting more water, you're making more conductivity. So there is a lot of things which people are doing wrong in a thermal runaway event from a safety perspective. And this is a very important part of the awareness about thermal runaway, which I wanted to maybe give here, because mechanical abuse, electrical abuse, and thermal abuse, all of them have happened in many cases. I guess you all heard about the Boeing case, which we had a battery going on fire on it. Crashes which did go into thermal runaway, even cars going to fire without any kind of charging or discharging. Aging as well plays a big role into safety as well. But the main message here, I guess we'll not be able to cover all the aspects because of the time and details. The main message here is that dealing with the thermal runaway is not done correctly in the market so far. And not every chemistry goes into thermal runaway in the same way. I guess we mentioned that LFP may be a bit safer than other chemistries, but this graph here shows that maybe it goes into thermal runaway in higher temperatures, and it even produces less energy. But this is something which I guess we can discuss into coming up seminar. So I will stop here. I will get back to this is how we deal with some thermal runaway cases, putting a car inside a container for some days, for example. And I will get back to the value chain. Here, and open the floor for any questions. I guess we have given a very intense amount of information, and there are much more information maybe we can cover in the next seminar, but I'm very thankful for the opportunity. And if you have any questions beside the one which have been asked, please do. And thanks a lot.
Thank you, Dr. Mohammed. Thank you so much for this informative seminar. And now we will take the time to open the floor for more questions. So if anyone has a question, you can write it in the chat and I will read it, or you can open your mic and ask questions for Dr. Mohammed.
Sure, yes. But the first thing which I would like to get to is that there was in the chat a question of explaining how the knowledge of production affects the degradation. And I would like to comment here about this question. And if there is any other question, please let me know. But to make clear, the battery manufacturers really did see the value of tracking data. And there is as well an EU regulation, European regulations for doing something called battery passports. It's an obligation which more or less will come into a standard or a law that you have to gather your battery data from different parts in the value chain and submit it whenever it's needed, for example, for a second life application. And it's, I guess, 150 pages of regulation just about gathering data and creating a battery passport for the second life. This is one of the things which is related to this question. The second thing which I did not show, but it's very important as well to this question, is this standard here. So this is the UL 1947. It's a standard which came recently of creating a safe second life for electrical vehicle batteries. And it's an attempt from the UL, or a first step from the UL, to create a standard related to how we can standardize the second life applications.
So I have a question related to second second life batteries.
Mhm.
So you mean you take the batteries out from EVs after their lifetime and you use it as a community energy storage, for example?
Yes, that's right. This is the process, as you can see it here. You take you have a battery which is have been an EV in an EV, for example, and because in an EV you need a lot of power and energy. You stop at a certain level, which we call it 80% relative capacity, for example, but still there is energy inside the battery. So you start to make a disassemble process and evaluation process and safety evaluation, aging evaluation, electrochemical prospectability, approved or rejected, and then you create another battery out of it. But of course, on a cell level, this is very hard to distinguish cells, but maybe on module levels, we can do this.
Okay, and the battery will be removed from the car when its life is like 80%. It can hold only 80% of its.
Of its original capacity, yes. So this is the common practice. I will show you a graph here from the aging part. The common practice is 80% relative capacity, but just to make sure that we all understand the relative capacity, I guess this graph here was from KIT. Yeah, was an analysis. So you have number of cycles, and you have, for example, your battery at the beginning of life can store 100% of its energy, 100% of its capacity, whatever what is the capacity is in ampere hours, and then it goes to 80%, and this is where you have the more or less the end of first life. It's end of life, but some people take it as an end of first life. Some people even tries to push this to 70%, 75% farther down.
Okay, and how fast you go to this 80% limit? It depends on how harsh you are using your batteries. It's the depth of discharge, how frequent you are charging your battery, correct?
Yeah, but the depth of discharge is one thing. So the depth of discharge plays a role for sure. And this is the number of cycles which you do. But all the aging mechanisms plays a role as well. So the aging itself is not only a one factor thing. It's really like a 4-5D matrix. It's very complicated thing. So it's a combination of what type of quality did you produce with, and so on, and how you operate your battery, both of them. So
I have like a general question, and I want your thoughts on it. So I hear a lot that it's better to keep your phone battery above 80%. Whenever it goes below 80%, you charge it again, so you can extend the lifetime of it.
Oh,
Is it
no, this
correct?
is it's no, this is totally wrong. It's a totally opposite. And that's why my phone here, I have the limit of maximum charging to 85%. For current lithium based batteries, it's not good to go to 100% charging. This is what we call the cycle aging. So you have opened a very good question, or you have opened a very good field. So in aging in general, we have mainly two effects. Let me just answer your question by going to the aging part here. So aging happens by capacity loss and resistance increase. So the cell itself, its resistance increases, so you cannot get a lot of current out of it, or you lose capacity by time. So for example, for a phone, let's take it as an example. Your phone started after two years of life, maybe 1 year in some bad users, to not complete even 1 day on full charge. Correct? Sometimes it happens, and this is because this.
Yeah, maybe 6 months. Yeah.
Maybe in 6 months, yeah. And this is because one of the things which you said, which is totally wrong, that you are keeping your phone in very high state of charge a lot of time. No, it's the opposite. You have the best case is that, if we can generalize, is 20 to 80%. You keep your phone between 20 and 80%. And that's why, for example, if you have an iPhone, if it goes below 20%, it will tell you, okay, power saving mode is on. And if you go to 80%, the iPhone will tell you, okay, I'm full. Please remove me. And if you go to 90 to 100%, you start seeing that the phone is taking maybe a longest time to charge this, only 10%, rather than the whole spectrum. And even in Android phones like myself, I can tell the battery, please stop charging at 80%, 85%. I do this to my laptop. I do it to my phone. I do it to everything, that I stop charging at 80%. Otherwise, after 6 months, 1 year, you are stressing the battery, because at the end, it's like, if we can simplify it, it's like really stressing the battery itself, because what really happens in the battery itself is like, if I can go to the big graph here, this is the aging mechanisms which happens inside the battery. This is the cathode, the anode, and the SAI layer and the electrolyte. But this is something which we can discuss in the follow-up seminar. But it's like if you are overcharging your battery, or if you're charging it a lot, it's like trying to getting these balls here, which are the lithium ions, inside the cathode and making cracks and even building dendrites. So it's one of the common, but it's not only you or someone else who has this wrong information. It's a common practice, because it comes from the previous technologies than the lithium-ion battery.
Yeah, so the silly question is, if I'm only charging it to 80%, does this be considered as 80% energy? What is the difference between that I have to change the battery when it reaches 80% of its energy storage capacity, compared to I'm only keeping it at 80%? So the useful side is still 80%.
Yes, but this is 80% state of charge, and this is 80% relative capacity, which means, let's imagine that this is the cell, huh? Okay, and 80% state of charge means that I'm charging it to 80% of what it can accept. Correct?
Yeah.
I'm doing this, I'm cycling it to this, but this can, let's have an example of that this battery can accept 100 ampere hours. So the state of charge, there are two different types of state of charges. There is a state of charge of energy, and there is a state of charge of capacity. So it depends on how the voltage curve of the cell is. So the state of charge which you see is not the state of charge of the energy, which is the relative capacity. Is the state of charge which is calculated based on the algorithm going through the amount of energy you have put it inside the battery, which is more or less the middle of the curve of the voltage of the battery itself. So there is a bit of difference in some chemistries, that the state of charge energy doesn't match with the state of charge of the capacity. So both points are not the same, but maybe this needs really that I draw the graph for you and explain it. I explained it in one of the series in the battery series, which I did put online. But it's a very good question, which we can as well explain it maybe next time. But at the end, what we are stopping it here, this is the relative capacity, which means that I cannot put any more 100 ampere hours here. This battery goes to 100% SOC by accepting only 80 ampere hours, not 100 ampere hours anymore.
And in this case, the optimal is to charge it to 80% of this 80%.
Exactly.
85%.
Yes, now you got it very correctly. Yes. In this case, you have to charge it to 80% of the 80% left of capacity.
Okay.
Yes, that's correct. And that's why applications like electrical vehicles, for example, they are not interested into the state of charge of the capacity. They are interested in the state of charge of energy, because they want to know how much I can go as mileage with my car, not how much I did pump in or out of my cell. No, I want to see how much really I can go in kilometers. Yeah, but very interesting question. I guess we can cover this in the follow-up seminar. But but please do not charge your battery like 180%. This is not the correct way to do it.
It's too late. I killed the battery already in 6 months. So.
Okay, so after 6 months of doing this, you killed it.
Yeah.
But it's good. That proves that the info is correct for other people.
Is there any other questions from the attendees?
No, I don't see any other questions. I guess it was more than enough information. If you have a question yourself, just do it. Otherwise, I would be more than happy to do a follow-up seminar for sure.
Sure. Okay. Thank you, Dr. Muhammad, for taking the time and offering this informative seminar for IEEE KW. And we will be planning another follow-up seminar when your time permits. And thank you for all the participants that attended today. And I hope you enjoyed the seminar and get information from Dr. Muhammad. Thank you so much.
Thanks a lot. Thanks for the invitation. It's a pleasure always to be in the IEEE and WISE specifically. And for sure, we will have a follow-up. Thanks very much for the opportunity and the time. Have a great day.
Okay, thank you.
Thanks a lot. Bye-bye.